Good afternoon, everyone. Welcome to the joint seminar of GQFI and the Warsaw String Theory. Today, we are very happy to have Alice Di Tucci from Max Planck Institute for Gravitational Physics. So she will tell us about some lessons for quantum cosmology from anti-de Sitter black holes. So take it away, Alice.
Thank you very much, and hello everyone. Thank you first for the invitation. I'm extremely happy to be talking here today for this very nice series of seminars. So yes, I will be talking about lessons that cosmology can learn from black holes in anti-de Sitter space. So this talk will be based on work that I've done and is still ongoing together with Michael Heller and Jean-Luc Lehners here at the AEI. And here you can see the reference to our paper that came out last summer on this topic, where, so the general question that we wanted to ask in this project was how to understand gravity path integrals beyond the saddle point approximation. In fact, for sure, in most situations, one is really interested in the saddle point contribution. For sure, in holography, it is the saddle point approximation of the path integral, which is in most cases related to the partition function of some dual quantum field theory. And it's in cosmology as well. Very often one is interested in making just semi-classical considerations. But then there is a question of how is the full path integral actually defined? What is the saddle point really approximating? And this is an important question because this is what ultimately defines what is the physical setting that one is describing. That's why we started looking at the boundary conditions and integration contours for path integrals with applications in cosmology and holography. But again, I think this is a question that is of relevance for in any situation that wants to talk about gravity semi-classically. And I want to stress from the start that we make a very strong use of the Minisuperspace approximation, which means that we consider class of metrics which have a very high degree of symmetry. And this is what allows us to actually calculate the path integral in various situations. And so this is very nice. On the other hand, this is an approximation, and we are aware of the fact that the validity of this approximation itself can be put under debate. So we try to always keep an eye on this. And in fact, we try to look for situations where we can actually test the validity of the approximation itself. And so I will talk about this, referring to applications to the no boundary proposal for cosmology. And then I will talk about black holes in anti-de Sitter space. So I will start discussing cosmology, maybe for the next 15 minutes. So this will be an introduction. I will give a review of the status of the art there. And then this will serve as a motivation also for our black holes calculation. So in cosmology, the gravitational path integral will give you the wave function of the universe, which defines probabilities for fields configurations on a space-like surface. So why is it even important to calculate that? Well, let's look at this picture on the right for a second, recalling that in cosmology, ultimately the question we want to answer is what happened in the early universe. And a piece of data from observation that we have at hand to do that is the cosmic background radiation, which are represented here, on which we see correlations among inhomogeneities of temperature, for example. So the question of what happened in the early universe is actually a question of how these correlations are generated and what is their history. Then the story goes that most of the scientific community believes that much before that, the universe underwent a phase of accelerated expansion. which we call it's called inflation, and during which our universe basically looked like a portion of de Sitter space. And the point about this is that the energy scale during inflation can be extremely high. It can get as high as 10 to the 14 GeV. So all sorts of high energy and quantum effects are expected to possibly have happened in this phase. And that's why we need to refer to this formalism of the wave function of the universe, which is an object which is defined here on the surface in time where inflation ends. So the wave function of the universe takes values here and gives us a probability for the given field configuration there. And then we can use it to calculate cosmological correlators, the usual way that I represented here. We can use this modulo squared. If we integrate it with 2 powers of a field, this would give us the 2-point function for that field, 3-point function, and n-point function. So then this is the theoretical data that then we can kind of evolve forward in time and try to compare with the CMB, with the ultimate goal of possibly being able to look for signals of these high energy effects, which could have happened in this phase, on the CMB. But how do you actually calculate this wave function? Well, for sure, this is can be given as a path integral. Actually, do you see the browser if I move it?
Yes, we see the browsers.
Okay, thank you, sir. So the wave function will depend on some field configuration, which I call generically F, which lives on this surface where inflation ends. And you can think of it as being given by a sum or a history of whatever could have happened before to bring to that configuration. Another way possibly to calculate such wave function is to instead completely forget about this cosmological bulk and only make boundary consideration. This is because the wave function, after all, lives on this space-like surface and doesn't know anything about the bulk in principle. So you can also just try and calculate it and bootstrap it, just looking at the boundary. But the point I want to make here is that in both cases, whatever approach you like the most, everything in your results is going to depend on which initial conditions you take, which is obvious from the path integral point of view, but also if you want to just look at the boundary, still there's going to be an external assumption which corresponds to which initial conditions you take. And this is maybe something that one might not be so familiar with in the holography community, as for example, I don't know if one is talking ADS-UFT, ADS truly has only one boundary. So what happens in the interior, it doesn't really affect, or in a sense, one can just take some regularity condition in the interior to make calculations at the boundary. But in cosmology, you know, a generic cosmology will end up in a singularity in the past. Or if you want to think of de Sitter space, this really truly has another boundary in the past, together with this future boundary we're interested in that is here. So really imposing what happens there is important and will affect your calculations. So we need an external assumption. And so what most of the community does in cosmology, and seems to really also agree with observations, is to make the assumptions that fields start out in the Bunch-Davies vacuum. That is a sort of a regularity condition, but on a particular type of geometry, which is the Hartree-Hawking geometry, which I represented here. The wave function of the universe should be picked around this geometry, which has the property, as you can see here, of kind of getting rid of one boundary. So this geometry really has only one boundary in the future, and there is no problem in the past. You have kind of closed it smoothly. And this Bunch-Davies initial condition is the condition that fields behave regularly here at the South Pole. And this, the fact that the wave function of the universe should be picked around this geometry goes under the name of the no boundary proposal. I just wanted to describe briefly a bit more this geometry by noticing the following thing. So this the future boundary is where inflation ends. That's where the wave function takes values. And this green part of the geometry describes a Lorentzian de Sitter space, which in fact in close Ising is just an hyperboloid, which I is drawn here. But now, if we want to close this geometry regularly, we need to consider a Wick rotation and go into Euclidean time. And in fact, the Euclidean version of the Sitter space in 4 dimensions is 4 spheres. So you take that 4 sphere, you take half of it, and you glue it at the waist of the hyperboloid. In fact, the two match at the waist. And with this construction, you can then get this smooth geometry, which has only one boundary. And but for this, it's absolutely essential to go into Euclidean time. And you know, having said that, already Arden and Hawking 40 years ago, when they proposed this, they asked the questions of, well, for sure, the function should be at the saddle point level, be given by this geometry, but how do we define the entire wave function? How is the gravitational path integral actually defined? And you know, quoting Hawking, he would take this saddle point geometry very seriously and tell you that, well, the boundary condition of the universe is that it has no boundary. This is absolutely obvious from this picture. And then, you know, they went on saying that our proposal is that the sum should be over compact geometries. This means that the universe does not have any boundary in space or time. So this sum should be a sum over compact geometries. And there is another way to look at the same geometry or wave function, but giving it a different interpretation, which is also very suggestive, which is to think that, you know, time runs from down up in this picture. So here is the final very large classical inflating universe we obtain. But if you go back in time, the universe is shrinking all the way to 0 size. So the South Pole would correspond to a 0 size geometry, which they call nothing. So in a way, this wave function is representing a finite classical universe coming out of nothing due to a quantum effect. The fact that it's a quantum effect comes crucially from the fact that we had to go Euclidean. So this wave function will have a real part. So this will give actually a quantum weighting for this process to happen. So this is, in this sense, this is describing really the initial condition of the universe, a universe coming out of nothing. But then, you know, can we actually do this integral? Can we say anything else about it? Well, the good news is that one can do the integral in very, I mean, the simplest of settings possibly, probably, which is considering no other form of matter, just gravity with a positive cosmological constant in the Minisuperspace approximation. This means that in this path integral, one does not sum over all possible sort of geometries, but over geometries of an FRAW type. So geometries that are homogeneous and isotropic. So taking these ansatz in particular. So which might not be the most familiar way of writing the FRAW, but is particularly convenient for doing these calculations. And from this ansatz, you can see that constant times lattices are spheres. This is an element of a unit sphere. These are spheres of radius q. I try to represent this in this picture. We have the time variable t, which runs from 0 to 1. And at t equal 1, we fix a sphere of a radius q1, which we take to be very large. Now, now the path integral will then be given by a sum over all functions q and all values of the Laplace function n. We need to impose this condition of what is the final radius of the sphere here, and some other condition at the time equals 0, which I'm gonna come back in a second. Then making up evaluating a path integral means to summing over all sort of histories, which are represented with these lines here, which interpolate between these two surfaces. And the sum over all values of the lapse n means summing over all time separations between these two surfaces. N precisely gives the proper time separation between the two. So that's what the calculation that we effectively do. But let's talk about the condition we need to impose here now. So I don't want to go into many details of this calculation, but you can see here, these two equations are the saddle points equations. So these are basically Einstein's equations for this type of metric. And I wrote them here because from this constraint equation, you can see the following. If you want Q to be 0, so if you want your geometry to start at 0 size, then you need to, the momentum then needs to be plus or minus I. As we knew, like we knew that we had to go Euclidean if we wanted to close the zeta space in a smooth way. And crucially for the no boundary proposal, one needs to select the plus I sign, because this corresponds to making a Wick rotation into Euclidean time in the correct direction, which is important. The Wick rotation has to have one specific direction. So you see, from the point of the saddle point, there is at least two different things that one can do. At least two different conditions that one can impose here. I can impose that the geometry starts at 0 size, or that it starts with this plus I momentum. And this will, of course, dramatically change what the path integral is, but will not change the saddle point geometry, of course. So the first case is the case of a path integral with Dirichlet boundary conditions on both surfaces. I fix the 3 geometry on both surfaces. And in order to do that, one needs to include, together with the Einstein-Hilbert action, also the York-Gibbons-Hawking surface term on both surfaces. And this seems to be, this will give you a sum over all geometries will start at 0 size, and unfortunately will not give you the right result. In fact, we'll give you, in the saddle point approximation, another geometry, which is the complex conjugate of the Hawking one, and does not bring to the nice Bunch-Davies initial condition that we need for cosmology. And this was shown, highlighted in 2017 by Feldbrugge, Lenners, and Turok. Whereas the other possibility of mixed boundary conditions does work. One can impose a Dirichlet condition on the surface, fixing the size of the final sphere and fixing the momentum on the surface to be equal to plus I. Then one has no boundary term on the initial surface. And this path integral, in fact, will give you the Hartle-Hawking wave function. But you know, like, and this specific fact started quite a bit of a discussion in the cosmology community, because this goes quite a bit far from what was the idea of Hartle-Hawking actually for this wave function, because this was describing, if you want, a universe starting out of nothing. This would be describing a universe which starts out of a momentum, Euclidean momentum space. It's much less clear what this actually means. It's much less clear whether this is really describing the initial conditions of the universe, conceptually. But this turns out to be the right thing to do. And this is why we started looking for analogous situations where one can actually test this idea of using no boundary term in the interior of this initial surface and imposing a Neumann condition there. So this brings me to the black hole calculation, and I don't know if you have a question at this point. Okay, if not, we'll continue. So again, the motivation for doing this calculation for us was to check whether we could make sense of this Minisuperspace calculation with mixed boundary conditions in a context where we actually know the result. In particular, if we do a calculation for a path integral for black holes in Euclidean anti-de Sitter space, then we expect to recover something like the Hawking-Page phase transition. Then I will show you that this is in fact what we recover. So we look for we're calculating a path integral in the Minisuperspace approximation with a negative cosmological constant now, where then this will represent a partition function for an S1 crosses to Euclidean boundary. Now, in this case, the Minisuperspace ansatz will be different. In fact, will not be of FRW type, but of the type of Kantowski-Sachs, which looks like this. Where now everything depends on R, which is the radial variable. So at R equal 1, we encounter the boundary, whereas R equals 0 will be the point where our geometry starts. And we have now two scale factors, C and B, and the analogous of the lapse function. Now, the Schwarzschild black hole in Euclidean ADS clearly belongs to this class of metrics. And you can see this by, if you take these values for the various functions involved. So this will be, RB, clearly is the radial, effective radial coordinate and runs from R+, which is the location of the horizon, to some value R2, which is the size of the two sphere. So only taking this R2 to infinity will then allow us to cover the entire ADS space. So we will do that eventually, but we are also interested in looking at effects which come from cutting ADS at a finite radius. Then if B is the radial coordinate, you can recognize from how it's written C that this is a Schwarzschild black hole, probably, and where the mass, the M is the mass and is related to the horizon in the usual way. And it's also important to stress that in order to make this geometry regular, one needs to periodically identify the time variable. So the time is periodic with period beta, where this beta is related in a particular way to the horizon size to get rid of the conical singularity. And another thing that maybe you're not really familiar with is the fact that there is a minus sign here. So this geometry looks Lorentzian. But in fact, in the path integral, it will be summing over complex geometries anyways, which are not Euclidean and not Lorentzian. So this doesn't really matter. But indeed, n is imaginary at the saddle point. So this solution then will be Euclidean, as it should. So this is the solution we are looking for. We're going to sum in the path integral over all sorts of metric, all metrics of this type, and look for these solutions at saddle points. But before doing that, I wanted to stress again which type of boundary conditions we impose. That's ultimately what we are mostly interested in. And so at the boundary, we consider Dirichlet conditions. So we fix the radius of the circle and the two sphere to be R1 and R2. And of course, we are fixing the temperature then of the dual quantum field theory. So we will expect the partition function to be that one of a canonical ensemble, and we'll have to verify this. Whereas at the inner boundary, what I call the inner boundary is this location R equals 0, we want to impose a Neumann condition, so to put no boundary term. And this is because precisely we want to test this assumption that we had to do in cosmology in order to make the no boundary proposal work. And it turns out that taking no boundary term makes the variational principle compatible with the following type of boundary conditions. So we can take the geometry to start at the horizon. So we can take C of 0 to be 0. And you can see from here that C being 0 is exactly the location of the horizon. And together with that, we can impose another condition, which is this one here, which in fact turns out to be the condition for the geometries we sum over to have no conical singularity. In fact, at the black hole saddle point, this just looks like this, which is the usual way in which one can get rid of the conical deficit for black hole solutions. But this is really surprising and extremely nice that just like in cosmology, also here we can impose the Neumann condition as a regularity condition. In fact, it is the same as requiring that the geometries in the path integral do not have a conical singularity at the horizon. It's really nice. So now we have all the ingredients to actually do the integral. We know the boundary conditions and we know the class of metrics we are summing over. So I will now sketch what our results were. And again, to evaluate the path integral, we need to integrate over the scale factors C and B, and these are Gaussian integrals that we can just do. And together with that, we did careful steepest descent analysis of integration contours, because of course we want to make sure that the integral we're discussing actually exists. And this we had to do numerically, because we couldn't have a really an analytic handle of the calculation at this point. And this is represented in this picture, where you see the complex n plane. And these arrows represent precisely lines of convergence of the integral. So if you follow an arrow, you will go to infinity into a region where the integral converges. In red, you see the saddle points, which very surprisingly, if we start the calculation at very high temperature, these saddle points are 5, which we didn't expect at the beginning. In fact, like 2 are the saddle points that we expected to find, so the large and the small black holes, because the solution exists for a high enough temperature. And these solutions, by the way, are Euclidean. In this complex n plane, here is in the imaginary axis will be, of course, the axis where the geometries are Euclidean, and this will be the Lorentzian axis. And this 2 black hole solutions belong to this class of our Euclidean solution. Together with these 2, where we have another Euclidean solution, which is irregular, and 2 complex ones, which are represented here. This we didn't expect. And in fact, I think this is an interesting prediction of this calculation, as shown in this picture to the right, where I'm representing the weighting of the various saddle points as a function of the radius of the sitter. So the larger R2, the limit where R2 is infinity, I push the boundary of the sitter to infinity. Oh, sorry, until the sitter. And you can see that the large black hole saddle point always dominates over the small one, over the singular geometry as well, and the complex ones, which have the same weighting. But what is very important to notice is that in this limit where R2 goes to infinity, these spurious saddle points are completely suppressed. They're actually exponentially infinitely suppressed. So the fact that we see these extra saddle points is completely an effect of having cut ADS to a finite radius. And one thing that it would be extremely interesting, I think, to have an holographic description of the saddle point to understand what they mean from the point of view of the quantum field theory. And because this would then kind of support the use of this Minisuperspace approximation or completely rule it out. This calculation gives an element of falsifiability of this Minisuperspace approach, because if these saddle points are not there, then this calculation adds something simply wrong in it. So I think this is extremely nice. And the last thing I wanted to add on this is that it's on integration contours, because of course now we've seen which are the saddle points. We need now to define where the path integral is defined. And the first thing to notice in this sense is that if you cannot do a Euclidean integral. In fact, if you follow from the origin into the negative, for example, imaginary axis, you would go against one arrow. So you would end up in origins of divergence. And the same is actually true for the Lorentzian contour, even if it's not shown by the arrows in this case. So actually the integral cannot be Euclidean or over Euclidean or Lorentzian matrix, but it has to be intrinsically complex. And in this case, we're kind of forced to one contour by knowing the solution. So we need we know that the partition function will have to be picked around the black hole saddle points. And this means we need to take precisely this contour here in dotted line. But I have to say that in this case, we do not have a real good intrinsic reason for making such choice. This is basically motivated by knowing already what the result is. This is another thing that probably it would be good to clarify in the future.
Can I ask a question?
Yes.
Yes. So these additional saddle points that you find, they appear only when the boundary is at a finite distance, right? Of finite radius. Yeah.
Yes.
So is there any thermodynamic interpretation of these saddle points as were contributing to the thermodynamics of the black hole when the black hole is in a finite box in ADS? Or is that something that's not at all the right way to think about it? And you know that you could put, and you can consider black hole thermodynamics, where instead of having the boundary at infinity, you put some boundary conditions at finite distance. This is something that you can do in Minkowski space, and that it gives something similar to ADS, but here you're doing it in ADS. So, and that's a black hole in a box of finite radius as you impose some boundary conditions. I think that this need not be related to these saddle points, but let me say that my question is there a thermodynamic interpretation to these saddle points that you have, that you're aware of? Or?
That we do not have, in the sense of we see they are there, and especially if we have to take this contour, they are truly there, but the partition function is always, in fact, dominated by the large black hole.
Yes.
So then when we went on into doing a thermodynamics analysis, we actually then focused on that one particular black hole. So it would be, of course, extremely interesting to try and interpret those in some sense in that.
Thermodynamics, right?
I do not, yes, but it's not something that I have an answer for at this moment.
Yeah.
Yeah.
Yeah, and the dual interpretation that you mentioned, that would also be, I mean, the interpretation in ADS CFT, but where you have a cutoff for the CFT. Would it be something like that?
Yes, because again, this is an effect that we see with when ADS is cut at some finite radius. So this will be, potentially an interpretation in terms of some deformation of a CFT. But this is not something that, again, we don't know. We just notice that this exists, and that, and therefore it would be extremely nice to investigate a bit more.
Okay, thank you.
Thank you for the question. So then, having said all this was a discussion of these flow lines for a very high temperature. We're now after the Hawking phase transition, so we're gonna lower the temperature and see what happens. I'm gonna show, in this slide, I'm showing flow diagrams for decreasing values of the temperature. And we see that at first, the large and the black hole saddle points just come closer to each other, and at some point they merge. And and we find that the temperature at which they merge is the correct one. I mean, it's the one that one would expect for the Hawking phase transition, where of course here there are again some corrections that come from having cut ADS to a finite radius. And then the way that we see part of this phase transition in this setting is that if you go to even lower temperatures, so beyond this limit, the saddle points, which were the black holes, now become complex. So we do not have Euclidean black holes solution anymore. And so this is, I think it's already extremely nice that we were able to reproduce this. And the last piece that is missing in this calculation is a comparison with the empty ADS solution. So somewhere in this regime, before the saddle points become complex, where the partition function is dominated by the large black hole saddle point, we can now compare with the ADS solution, which is what I'm showing here. So the difference in action between black hole solution and ADS1 is given by this slightly configured expression, which reduces to basically the usual result up to corrections given by the radius of ADS. And so we also recovered the fact that the ADS solution dominates if the temperature is low enough, or if the radius of the black hole is small enough. So somewhere here, somewhere before the saddle points become complex, actually the ADS solution comes to dominate. So we have actually recovered the Hawking phase transition, and we can go on into the thermodynamic interpretation, where here now then we focus only on this black hole solution because it's the one that dominates the saddle point, the partition function, even though, as we just discussed, the others are actually there. So it would be really nice to be able to include them also. So then the thermodynamics interpretation goes as follows. We just relate the partition function to the difference in action, and we evaluate the expectation value of the energy, the entropy, and we find that they satisfy the expected quantum statistical relation, where the area does not get corrections due to cutting of ADS, whereas the expectation value of the energy does. And we can then also calculate the conserved mass, which is the same as the parameter which enters the black hole solution up to corrections in the ADS radius. Now, why am I even saying this? In the sense of this is, in a way, all the well-known story. And the reason why I'm telling this to you and why this is very important is that it all works well because we added not Gibbons-Hawking your term in the interior. So we imposed a Neumann boundary condition. Had we used the Dirichlet condition, then we would have had an extra surface term, an extra contribution coming from the horizon of the black hole, which would be equal to this, or equal basically to the entropy. Then the partition function would have looked like much more partition function of a microcanonical ensemble rather than the canonical ensemble. I remember that we did fix the temperature at the boundary, so this would have given us the wrong result. So also here, just like in cosmology, it's absolutely crucial to impose mixed boundary conditions. So Dirichlet at the real boundary and Neumann in what you would call the interior to get the right result. And also in this case, the Neumann condition can be thought of as regularity condition, because it was, if you remember, the condition of having no conical singularity. So this, I think, it's already extremely nice, and it's a good support of what we had to do in the case of cosmology of the no boundary proposal. And we went on and verified this this assumption, or this proposal, if you want, in another case. in fact, we looked at the partition function for spheres. So this is actually the calculation that can be brought in one-to-one correspondence to the cosmology one. If you remember what I had in one of the first slides, this is the same class of metrics, more or less, except that now R is the radial coordinate, whereas in the case of cosmology one, you would talk of a time variable. And of course, here we're considering a negative cosmological constant. And so we learned now that in the path integral, we should not put any surface term, any Gibbons-Hawking-York term in the interior. So if you want R equals 0, because we want to impose a Neumann condition there. And in this case, we should add some counter terms to take care of the IR divergences in ADS. Because by the way, in this case, of course, we expect the saddle point solution to be Euclidean ADS with this S3 boundary. So the boundary condition we impose is that we fix the size of the sphere to be some finite value R3, which we're then gonna send to infinity. And we fix the value of the momenta, which I'm now gonna keep generic and just call it alpha for a second. And pretty much like I described before, we can evaluate this integral and making a steepest descent analysis of the complex end plane. Where without going into many details, what is important to notice is that once more, one cannot do the Euclidean integral. So if you try to go up here, you would end up with just something divergent. And in fact, in this case, what tells us which type of contour we should take is the fact that we know the answer should be real. Like we have to sum over complex geometries. We're forced to do that. But we know that in the end, the partition function would be the partition function of a Euclidean quantum field theory. So this should give us a real number. So after all, there is not so much that we can do. We are kind of forced to take this contour here. So the sum of this one, which is called psi1, C1, and psi2. And we can just evaluate the integral along this path. In this case, actually, even exactly. And this gives this expression here, which in the limit of where the boundary of ADS is sent to infinity, gives this exponential. And this is nice because now we can compare this result with already known result in the context of holography, which is the three-sphere partition function of the ABJM theory, which is given by this area function. And now wrote in terms of bulk variables, which in the semi-classical limit is just approximated by this exponential here. And you can see that the two coincide if we take alpha equal to I. And this is, again, extremely nice because this is just exactly the same condition we needed for cosmology. In fact, I will present the slide again here, but just to show you this is the same condition we need. So it seems that really like this condition starts getting universal, that we need to specify this type of Neumann kind of boundary conditions to make things work in various contexts. And so this is basically it on this topic. I just want to mention one last thing, which is the fact that in this case of the sphere's partition function, we could have actually done the calculation also with the Dirichlet boundary conditions. And I'm mentioning this because this is also, this relates to some work which has been done by Tsubut and Hirano in 2018, where they did the calculation in a very similar setting. And so we reproduced the result. And what is interesting to show in this case is that, okay, wait, first maybe I should say one can do the integral again in a very similar setting, calculating these flow lines and so on. But now with Dirichlet condition also in the interior. So setting the geometry to start at 0 size. And then, of course, also then putting this Gilbert-Hawking-York term there on the corresponding surface. This gives us the exact result, which in the limit where the boundary of ADS is sent to infinity gives an array function. That's something that already Saputo and Hirano noted, that this is exactly the array function that you have in AVGM. So they were wondering whether, then it seems that with this mini-superspace approximation, one can already just reproduce the full result. And this is in fact extremely nice. I would say that it is a bit, maybe one needs to be a bit careful with this, for the simple fact that, in this setting, one can really trust the value of the integral at the saddle point. It is extremely important to make an analysis of shell structures, or the configuration contours and the boundary conditions and all this. But in terms of the actual value of the integral, there is always this ambiguity of what the measure should be. So then in terms of what the actual result is, one can really mainly trust the saddle point. In any case, maybe it is nice to notice also that the Neumann result is the Fourier transform of the Dirichlet result, which is something that, of course, makes sense. The kind of quantum position representation of quantum mechanics is related by a Fourier transform to the momentum representation. So that's actually what happens here. But then, of course, these two results in the saddle point approximation coincide. So, so I think this is a point that maybe deserves a bit of further investigation to understand the role really of this array function in this context. So on this, we'll conclude by summarizing what my message was. And the main thing I wanted to communicate to you is that actually saddle point approximation can be subtle. One can, for sure, take the action, evaluate the saddle points, calculate it with the IES, and be happy with that. But in this way, you don't even know whether your saddle point actually contributes to the path integral you want to calculate. Or in other words, you don't know which kind of path integrals would then give the saddle point as the main contribution. And so whether this fits the physical situation you want to describe or not. And the other point I made is that mini-superspace approximation can really help in this case, because one can actually calculate things. And that one unexpected effect of using this approximation that we found in the case of black holes was the presence of these additional saddle points, on which that would be very nice to study more. Actually, on this, I also have to say that we could only do the calculations numerically at that point. So that's why, for example, we couldn't have a very good understanding of what the saddle points represented. And that's why now we wanted to look at, for example, largely limit of this calculation to see if in case anything becomes simpler there. And another thing that we discovered is that even though the saddle point is Euclidean, the gravitational path integral itself is not Euclidean nor Lorentzian. And this is something that you couldn't see from the saddle point alone, but it's something that has some, is just necessary. But of course, most importantly, we found that we need to impose mixed boundary conditions. So we need a Neumann condition in the interior, which can be thought of as a regularity condition and happens to be necessary to recover the correct black hole thermodynamics for black holes. And this was the same condition that we had to impose in cosmology to obtain the correct Hartle and Hawking wave function of the universe. So that's why we then say that black hole thermodynamics supports this implementation of the no boundary proposal. And with this, I finish. Thank you very much.
Thank you, Alice. Thanks for the nice talk. I think we still have some time to take some questions from the audience. So here is a question from Batu. Batu, can you ask your question by yourself? Or should I read what you have asked?
Okay, yeah, okay, I can ask, thanks. Thank you for the great talk. So my question is, in the ADS case, would you obtain the same result with the path integral over geometries with a single boundary, S1 cross S2, when you allow either the time circle or the two spheres to shrink to zero in the bulk, instead of imposing a Neumann boundary condition on the inner boundary? I mean, how important or how significant is the existence of the inner boundary? I mean, it looks to me that having a path integral with a single boundary and then allowing shrinking of the time circle or two spheres in the bulk would probably give the same result. What would you say about that?
So if you're referring to this case of the spheres partition function, that's what I try to say at the end, that we can in fact do the calculation thinking of having only one boundary. This would correspond to this kind of Dirichlet condition of having the initial size the initial surface to be zero. So then we would effectively have no boundary there. And this would give the same result at the level of the saddle point, because we would obtain as saddle point of this integral also the Euclidean ADS, but the full integral will be different. In fact, this Dirichlet calculation will give an AEI function, whereas the calculation with the Neumann condition would give this exponential. And the two are the Fourier transform one of the other. I don't know if this answers your question.
Yeah, okay. I'll take a look at your paper. Thank you very much.
Thank you.
Hi. I have a question. Does someone else want to speak?
Go ahead if you have a question. I will ask later.
Okay, thanks. So thanks, Alice, for the nice talk. I have a question regarding the regime of validity of the Minisuperspace approximation, which you mentioned several points. So yeah, the question is, what can you really expect to capture with the Minisuperspace analysis? So you mentioned the saddles, but you also have the complex plane. So what do you expect? What do you expect the Minisuperspace approximation can capture about the full gravitational path integral?
Well, I would say that that this is a bit of the question that we need to was answered. We need to still understand. I mean, that's I think a bit of the point, in the sense of this for sure will give you the correct saddle point contribution in case your saddle point belongs to that Minisuperspace class you're considering, of course. But it's not so clear what how much more than that this can tell you. So, for example, this was the point, the entire point, I think, of this result by Saputa and Irano was that in this particular case, you seem to recover the AEI function. So this will be an exact result in a theory with supersymmetry, extra dimensions, and all this. And somehow you seem to find it in the Minisuperspace approximation if you do the calculation exactly, which means if you do a calculation which is exact in H bar, even though you're shutting down infinitely many degrees of freedom. So if this is true, this means the saddle point approximation can actually tell you a lot. But I have to say that I suppose on this way, it's something that I don't have a definite answer. We need to, I suppose, still understand that. I don't know if this answers.
Yeah, all right, thank you.
Yeah, so I had, well, one generic question which was similar to this one about the Minisuperspace approximation. because I don't know if I recall correctly that, under what conditions this approximation could be a controlled approximation, a well-defined limit. My recollection is that there's a strong coupling limit, a strong coupling regime in gravity, where the gravitational coupling goes to infinity. That's when the Planck length also goes to infinity. Is that a limit that where the mini-superspace approximation becomes exact? Because I think that in that limit, spatial fluctuations are suppressed. So you get essentially something like homogeneity, only time dependence. Is that correct? Or is the, my question is there some limit where the approximation can be well justified?
It is in this limit where basically so in this limit where you're taking G Newton to be to 0, you are cutting
no, infinite. G Newton, you take it to be, it's the opposite of the conventional limit. That, as I said, that instead of being the limit where the Planck length goes to 0, that's the usual semi-classical limit. It's the limit where the Planck length goes to infinity, the Planck mass goes to 0. Everything, it's a bit like similar to the tensionless string limit in string theory.
I don't know. Honestly, instead, like the ways, so for example, there is a program by Kiefer where he tries to do this kind of mini-superspace approximation kind of systematically, but he expands in 1 over G. Yeah, actually, yes, in 1 over G. And he, in fact, from this exact formalism of the function of the universe, he recovers then at first order the mini-superspace result, second order, then he just starts seeing some fluctuations around that and go beyond the mini-superspace. So, yeah. But yes, then one thing that I can add on this is that probably this is much more kind of well accepted in the cosmology community, given that the universe is basically homogeneous and isotropic with tiny fluctuations. So doing this calculation, one is kind of happy enough if one finds homogeneous and isotropic saddle point around which perturbations are suppressed, suppressed with a Gaussian distribution. Then one, I suppose, says that the calculation can be trusted enough. Whereas of course, if you find that the perturbations are enhanced, as was the case of the no-boundary proposal with Dirichlet boundary conditions, then you have a problem with the theory, but with the mini-superspace approximation itself also, I would say.
And my other question was whether you have considered also charge in the charge black holes in ADS. Of course, when you have electric charge, then if you want to go Euclidean, then you have to, if you want real solutions, then you have to also weak rotate the electric charge. I think that this property that you find that you have to impose Neumann conditions, that's generic, that won't change. But in that case, I think that you will get more saddle points, richer behavior. I don't know whether that's something that you have considered or not.
The point with that is precisely that adding a charge, then the solution doesn't belong to this class of metrics we're considering anymore. So it would be extremely interesting to do, but then we need to find I don't know where I have it, a larger class of metric, which is not but that we can still handle and to do the path integral.
I think it would still be in the same class. Oh, no. Yeah, because here you have just two functions. No, you have three functions. Yeah, I'm not sure in this parameterization.
Don't we need the RT component in this case?
No. RT if you have a charge the ADS black holes. No, they can be also static and it's very symmetric. So I think, I don't know. I mean, if you have, I think, well, if if it's all parameterized by 3 functions, I think it's the same thing. I mean, you have to add the, well, up to a radial gauge. I think, yeah, I think it would be in the same class. I should check, but I think it would be in the same class.
Yeah, well, it's something that I cannot see immediately now. But
Yeah.
Yeah.
I think yeah.
It couldn't be in the same class, but I might be wrong.
Yeah.
Yeah.
Okay. I mean, just to know whether you have considered that.
No.
Okay. Thank you.
Thank you.
Anyone else who would like to ask a question? If not, let's thank Alice again for her nice talk. Thank you, Alice.
Thank you.
So now I will stop recording